At the heart of nearly every galaxy sits an incomprehensible cosmic monster. These supermassive black holes are the universe's ultimate enigmas, wielding power that bends the very fabric of space and time to its breaking point. By the end of our journey, you will understand 30 profound mysteries that challenge everything physicists thought they knew about reality. How did these giants appear so suddenly after the Big Bang? And what happens to the laws of physics at the very point of infinite density? Each question we explore pulls back another layer of this cosmic onion, revealing just how much we have yet to learn. What single mystery about our universe keeps you wondering late at night? These cosmic giants present us with a paradox from the very beginning of time. How could supermassive black holes, some weighing billions of times the mass of our Sun, have grown so immense when the universe itself was still in its infancy? We observe quasars, the intensely bright beacons powered by these monsters, shining from an era when the cosmos was less than 1 billion years old. For them to exist so soon after the Big Bang, they would have had to form and grow at a pace that defies our current understanding. This is the seed problem, a fundamental challenge to astrophysics. Where did the first seeds of these black holes come from, and how did they accumulate so much mass in what amounts to a cosmic blink of an eye? Our standard model of stellar evolution simply cannot account for this. A regular black hole forms from the collapse of a single massive star, but that process is far too slow. A star large enough to create a black hole might be, say, 20 times the mass of the Sun. For it to grow to 1 billion solar masses, it would have to consume matter at a ferocious rate. But there is a theoretical speed limit, the Eddington limit, which restricts how fast a black hole can feed without blowing away the very material it needs to consume. To solve this, scientists have proposed some extraordinary ideas. One leading hypothesis is the direct collapse black hole. Imagine a vast cloud of primordial gas, so massive and dense that it bypasses the star-forming stage entirely. Instead of fragmenting into many stars, this entire cloud, weighing perhaps 100,000 suns, collapses directly into a single, monstrous black hole seed. This gives it a colossal head start. Another possibility reaches back to the universe's first second. Primordial black holes could have been forged in the extreme density fluctuations of the early cosmos, providing ready-made seeds of various sizes. A third theory suggests the existence of supermassive stars, hypothetical behemoths hundreds of thousands of times more massive than our Sun. These stars would have lived short, violent lives before collapsing into the giant seeds needed. Each of these ideas pushes the boundaries of known physics, hinting that the early universe operated under rules we are only beginning to grasp. The very existence of these ancient quasars forces us to question if our models of cosmic growth are fundamentally incomplete, demanding either an exotic new mechanism or a rewrite of the laws we thought were set in stone. This paradox of cosmic origins leads us directly to an even deeper philosophical problem, one that strikes at the very heart of physics. What happens to the fundamental stuff of reality when it crosses a black hole's point of no return? This is the information paradox, a puzzle so profound that it has divided physicists for decades. It begins with a simple question rooted in quantum mechanics, the rules that govern the subatomic world. In our universe, information is never truly lost. If you were to burn a book, every single letter and word of that book is in principle recoverable from the smoke and ashes. The information is scrambled, but it still exists. Quantum mechanics insists this must always be the case. Yet, for a long time, black holes seemed to be the ultimate exception. Stephen Hawking made a stunning discovery, showing that black holes are not completely black. Due to weird quantum effects at the very edge of the event horizon, they slowly leak a faint glow of particles, now known as Hawking radiation. This radiation causes the black hole to gradually lose mass and, over eons, evaporate completely. The problem is this: Hawking calculated that this radiation is entirely random, carrying no information whatsoever about what fell into the black hole. When the black hole vanishes, all the information about every star, planet, or book that ever crossed its horizon vanishes with it. Poof, gone forever. This creates a catastrophic conflict. General relativity, which describes gravity and the large-scale universe, says information is destroyed inside a black hole. Quantum mechanics says that is absolutely impossible. Both theories cannot be correct. This paradox forced scientists to question their most basic assumptions. One of the most mind-bending proposals to solve this is the holographic principle. It suggests that all the information about everything within a black hole's three-dimensional volume is not lost inside, but is instead encoded on a two-dimensional surface at its boundary, the event horizon. Imagine the information of your entire life, every memory and experience, being perfectly stored on the flat surface of a credit card. If this is true, then the information never actually falls in. It is smeared across the horizon and could, in theory, be radiated back out, scrambled within the Hawking radiation. This idea, however, led to another shocking paradox, the firewall. If information is being encoded on the boundary, it might require a blazing wall of high-energy particles right at the event horizon, incinerating anything that tries to cross. But this contradicts Einstein's general relativity, which predicts you would feel nothing special as you crossed the horizon, a concept known as the no-drama principle. So we are left with a bizarre choice. Does information get destroyed, violating quantum law? Or does a fiery wall tear apart any object approaching the black hole, violating relativity? After decades of debate, the consensus is slowly shifting toward information being preserved, but the mechanism remains one of the greatest unsolved mysteries in theoretical physics, a ghost in the machine of our universe. This conflict between quantum law and relativity forces us to peer into the ultimate unknown, the very core of the black hole itself. At the center of these cosmic giants, according to Einstein's theory of general relativity, lies a point of infinite density, a mathematical concept known as the singularity. Here, all the mass crushed into the black hole is squeezed into a point with zero volume. Gravity becomes infinite, the curvature of space-time becomes infinite, and every single law of physics we have simply stops working. The equations spit out nonsensical answers, a clear sign that our understanding is fundamentally incomplete. This is not considered a real physical object, but rather a glaring red flag marking the boundary of our knowledge. It is the place where the universe declares that our current tools are no longer sufficient. So what truly resides at the heart of a supermassive black hole if not a singularity? To answer that, we must find a theory that unifies the realm of the very large, governed by general relativity, with the realm of the very small, ruled by quantum mechanics. This holy grail of physics, known as quantum gravity, promises to rewrite the rules for this extreme environment. One leading candidate is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating loops of energy. In this view, the violent chaos of the singularity might be replaced by a complex, stable structure often called a fuzzball. Imagine the intense energy at the center not crushing down to a point, but instead dissolving into a vast, tangled ball of cosmic strings, a fuzzy quantum state that prevents true infinite density. Another possibility is that matter simply cannot collapse that far. Loop quantum gravity, a different approach, suggests that spacetime itself is woven from a fabric of finite, discrete loops. This fabric cannot be torn or compressed into an infinitely small point. There is a smallest possible volume, a fundamental pixel of reality. In this scenario, the collapsing matter would rebound like a cosmic bounce, potentially giving rise to an entirely new universe within the black hole, a concept that turns these monsters into portals rather than in points. The most profound resolution might be the simplest, that true singularities do not actually exist in nature. They are merely mathematical artifacts, placeholders for a deeper physics we have yet to discover. What we call the center may be a dynamic, quantum-processed region where the fabric of space-time is reconfigured into a form we cannot yet imagine. Unlocking this secret would not just tell us what happens inside a black hole, it would reveal the very origin of space and time itself. The nature of the event horizon itself is a mystery wrapped in a paradox. This boundary, the point of no return, is not a solid surface you could touch. It is a ghostly membrane in space, a one-way door defined solely by gravity. Once any object, even a beam of light, crosses this invisible threshold, its fate is sealed. The escape velocity here exceeds the speed of light, the universe's ultimate speed limit, making departure fundamentally impossible. But what does it feel like to cross this line? According to Einstein's general relativity, you would notice nothing special at all, a concept known as the no-drama principle. The event horizon is a local phenomenon, and for an astronaut falling in, there is no sudden jolt, no flashing alarm. Space would simply flow inward, carrying you smoothly toward the unknown depths. Yet, for an outside observer, a bizarre relativistic effect takes hold. They would see you slow down, your image redden and dim, until you appear to freeze completely, smeared across the horizon for the rest of time. This stark difference in perspective is a direct result of spacetime being warped to its extreme. The reality of what happens to matter crossing this line is even stranger. An object falling toward a supermassive black hole experiences immense tidal forces, a process whimsically called spaghettification. The pull of gravity on your feet would be vastly stronger than the pull on your head, stretching you into a long, thin stream of atoms. These particles are not simply destroyed. They are believed to form a seething, hot plasma known as an accretion disk, a swirling vortex of doomed matter orbiting just outside the horizon. As these particles rub against each other, they heat up to millions of degrees, glowing brilliantly across the electromagnetic spectrum before their final, silent plunge. This is where the information paradox we discussed earlier becomes tangible. Does the information describing every one of those atoms truly vanish from our universe when they cross the line, or is it somehow preserved? Theoretical models offer wildly different descriptions of the horizon's properties. Some suggest it is a fiery firewall, a wall of high-energy particles that would incinerate anything approaching it. Others propose it is a quantum fuzzy sphere, or even a holographic screen encoding all the information of the interior. For decades, these ideas were purely mathematical. But now, we have our first actual glimpses of this mysterious boundary. The Event Horizon Telescope, a global network of observatories acting as a single Earth-sized dish, has captured historic images. Its first target was the supermassive black hole at the heart of the galaxy Messier 87, revealing a bright, asymmetric ring of light surrounding a dark central shadow. This dark shadow is not the event horizon itself, but its silhouette caused by the black hole's gravity bending light around it and capturing it forever. The size and shape of this shadow match the predictions of general relativity for a black hole of that immense mass, providing stunning confirmation that we are observing the effects of an event horizon. More recent observations of our own Milky Way's central black hole, Sagittarius A star, show a similar structure with glowing, knotted magnetic fields and hot gas whipping around at near light speed. These images are not just pretty pictures, they are data-rich maps that are already challenging and refining our models. They show us that the environment just outside the event horizon is a chaotic, dynamic maelstrom, a place where magnetic fields play a crucial role in shaping how matter falls in and how powerful jets are launched outward. Every new observation brings us closer to understanding the true nature of this ultimate cosmic border, a place where the laws of physics are pushed to their absolute limit. Those brilliant images of a black hole's shadow reveal more than a dark void. They hint at an even more violent phenomenon erupting from its poles. From the hearts of some galaxies, supermassive black holes fire colossal beams of matter and energy, stretching for thousands of light years into intergalactic space. These are relativistic jets, and their power is almost beyond comprehension, channeling energy that can outshine the galaxy itself. The central mystery is how a black hole, an object defined by its ability to trap everything, including light, can become the universe's most efficient engine for launching matter outward at nearly the speed of light. It is a cosmic contradiction that defies simple explanation. The secret does not lie within the event horizon itself, but in the chaotic maelstrom just outside it. Picture the accretion disk, that swirling vortex of superheated gas, as a vast, turbulent sea. As this ionized plasma spirals inward, it drags along immensely powerful magnetic fields, twisting and winding them into tightly coiled springs of energy. These magnetic fields become anchored in the disk itself, and as the black hole spins, it drags the very fabric of space-time around with it, an effect known as frame dragging. This rotation winds the magnetic fields even tighter until they form a rigid, rotating structure like a gigantic corkscrew extending from the black hole's poles. Some of the infalling plasma, instead of crossing the horizon, gets caught in these magnetic field lines and is funneled outward, focused into two narrow, oppositely directed beams. It is a cosmic particle accelerator on a scale we could never hope to build on Earth, where matter is whipped to relativistic speeds, converting gravitational energy into a focused torrent of raw power. This leads to the next puzzle. Why do some supermassive black holes, like the one in the galaxy Messier 87, produce these spectacular jets, while others, like our own Sagittarius, a star, are relatively quiet? The answer seems to lie in a combination of the black hole's spin and its feeding habits. A rapidly spinning black hole stores immense rotational energy, which it can transfer to the surrounding magnetic fields and plasma. Think of it like a spinning top. The faster it spins, the more stable and energetic it is. This spin is thought to be the primary power source for the most powerful jets. But a black hole also needs a steady, organized supply of fuel. If matter falls in from all directions in a chaotic, clumpy manner, the magnetic fields cannot become organized enough to form a stable jet. Our galaxy's central black hole is on a meager diet, with only sporadic snacks of gas, resulting in a much quieter existence. The presence or absence of these jets tells a story about the black hole's history, its diet, and its rotation, painting a dynamic portrait of these hidden giants. Understanding these beams of energy is not just about the black holes themselves, for these jets have a profound impact on their entire cosmic neighborhood, influencing how galaxies form, grow, and even die. Those immense jets of energy are a direct expression of a black hole's most basic properties, or at least what we thought were its only properties. For decades, the cornerstone of black hole physics has been the no-hair theorem. This elegant but unsettling idea states that a black hole is the ultimate simple object, completely bald, defined by just three numbers: its mass, its electric charge, and its spin. Every other detail, every shred of information about the stars, gas, or planets that fell in, is permanently erased, lost behind the event horizon. A black hole made from a collapsed star and one made from, say, a giant collection of rubber ducks would be utterly indistinguishable if they had the same mass, charge, and spin. All the rich, complex information that fell in is gone, leaving behind a perfectly smooth, featureless void. This is a profound statement about the universe, suggesting that an unimaginable amount of information can simply vanish without a trace. But what if this fundamental theorem is wrong? A growing chorus of physicists is now challenging this idea, proposing that black holes might, in fact, have hair. This is not literal hair, of course, but a metaphor for subtle, complex structures or fields that could linger on or just outside the event horizon. These quantum hairs would be faint imprints, preserving information about what fell into the black hole, encoding its history in a way that defies the classic no-hair theorem. Imagine the surface of a pond after you throw a rock into it. The ripples eventually fade, but a perfect, complete record of that event is still encoded in the subtle vibrations of the water molecules. Black hole hair would be like those lasting, microscopic ripples on the event horizon itself. One compelling proposal suggests that incredibly fine gravitational fields, extensions of the gravity from the objects that were consumed, could remain tethered to the horizon like strands of hair. These fields would be vanishingly weak, but they would carry a fingerprint of everything that ever crossed the boundary. This idea completely transforms the information paradox. If black holes have hair, then information is not lost after all. It is not destroyed inside the singularity, but is instead preserved on the surface, potentially radiated back out over eons through Hawking radiation. The paradox vanishes and quantum mechanics is saved. The challenge, of course, is proving it. How do you detect something so subtle from billions of light years away? The answer may lie in the most violent events in the cosmos, the collisions of black holes. When two black holes spiral together and merge, they shake the very fabric of space-time, sending out ripples known as gravitational waves. Our observatories like LIGO and Virgo have already detected these waves. According to the no-hair theorem, the resulting black hole should quickly settle down into a smooth, bald state, its gravitational wave signal fading in a simple, predictable ring down. But if the black hole has hair, the story is different. The presence of these complex structures would affect how the newborn black hole vibrates. Its ring down would be more complex, carrying faint echoes or modulations in the gravitational wave signal, subtle whispers of the information encoded on its surface. Scientists are now meticulously analyzing the data from these collisions, searching for any deviation from the simple ring down predicted by a bald black hole. Finding even a hint of an echo would be revolutionary, the first direct evidence that black holes are not the simple, information-destroying monsters we once thought, but are instead complex entities that guard the secrets of their past. It would mean that every supermassive black hole at a galaxy's center is not a blank slate, but a cosmic archive, its surface etched with the entire history of its violent growth. If black holes can have hair, perhaps they also hold a key to the universe's greatest ghost. Dark matter, that mysterious substance that outweighs all visible matter 5-1, reveals itself only through its gravitational pull, shaping galaxies and bending light. For decades, it has been a puzzle entirely separate from the study of black holes. But what if these two cosmic enigmas are deeply intertwined? One provocative theory suggests that dark matter might actually be made of black holes, not the supermassive ones at galactic centers, but of countless primordial black holes, smaller than an atom yet as massive as a mountain, forged in the first chaotic moments after the Big Bang. These ancient relics would be floating everywhere, invisible and nearly undetectable, their collective gravity accounting for the dark matter we observe. If this is true, then every galaxy, including our own, is swimming in an unseen ocean of microscopic black holes. Another idea proposes that dark matter is not the black holes themselves, but that it interacts with them in profound ways. Imagine dark matter particles swarming around a supermassive black hole like a dense, invisible atmosphere. As these particles occasionally collide and annihilate each other, they could inject energy into the surrounding gas, influencing how the black hole feeds and grows. This dark matter halo might even regulate a black hole's activity, acting as a hidden thermostat that controls its brilliant outbursts. The search for evidence is on. Astronomers are scouring the skies for telltale signs. One method involves gravitational microlensing, watching for the brief brightening of a distant star when an invisible, compact object, like a primordial black hole, passes in front of it, bending its light. So far, these surveys have not found enough of these tiny black holes to account for all the dark matter, but the hunt continues. Other researchers are looking at the very first supermassive black holes. Their incredibly rapid growth in the early universe might be explained if they formed at the centers of especially dense clumps of dark matter, providing a massive gravitational anchor that pulled in normal matter at an astonishing rate. The relationship might even be a two-way street. The powerful jets erupting from active black holes could be heating and dispersing the dark matter in their vicinity, preventing it from collapsing and thus shaping the entire structure of the galaxy that forms around it. Unraveling this potential connection is like trying to solve two separate jigsaw puzzles with pieces that might belong to both. Finding a definitive link would be a monumental breakthrough, finally giving a form to the formless and revealing that the universe's most dominant substance and its most destructive objects are part of a single grand cosmic story. This cosmic conversation between a black hole and its galaxy is one of the most profound discoveries in modern astronomy. It seems impossible that an object millions of times smaller than its host could exert any real control, yet the evidence is undeniable. Astronomers have found a tight correlation between the mass of a galaxy's central supermassive black hole and properties of the galaxy itself, specifically the mass and velocity of the stars in its central bulge. A larger black hole always seems to live in a galaxy with a faster, more massive stellar bulge. This is like discovering that the size of a tiny pebble in a city's central square perfectly predicts the population of the entire metropolis. The correlation is too precise to be a coincidence, pointing to a deep, fundamental connection, a symbiotic relationship where the growth of one is intimately tied to the growth of the other. But which one is in the driver's seat? Does the galaxy control the black hole's diet, or does the black hole govern the galaxy's life cycle? The answer appears to be a continuous feedback loop, a cosmic dialogue of construction and destruction. This dialogue happens through two primary mechanisms, often called quasar mode and radio mode feedback. In its youth, a galaxy is rich with gas, fueling both rapid star formation and a voracious black hole. As the black hole feasts, it enters the quasar mode. The immense energy released by the infalling matter, beaming out as light and powerful winds, blows away the surrounding gas clouds. This is the black hole acting as a regulator. By removing the raw material for new stars, it effectively shuts down the galaxy's star-forming factory, preventing it from growing too large too fast. It is a violent act of birth control that shapes the galaxy's future. Later in life, the galaxy enters the radio mode. Now the black hole is quieter, but its relativistic jets become the dominant influence. These jets pump enormous energy into the galaxy's halo of hot gas, preventing this gas from cooling down and falling back in to form new stars. This is a more gentle, heating-based form of feedback, a cosmic simmer that maintains the galaxy's retirement. Without this steady heat, the gas would cool, reigniting star formation and changing the galaxy's structure entirely. So does the tail wag the dog or the dog the tail. The truth is, they evolved together. The galaxy provides the fuel that allows the black hole to grow, and the black hole, in return, uses its tremendous energy output to control the galaxy's growth. It is a carefully balanced partnership, a gravitational tango that has been ongoing for billions of years. This explains why we see that correlation, the black hole and its host galaxy growing in lockstep, their fates forever entwined. This cosmic pact suggests that supermassive black holes are not mere passengers in galaxies. They are the architects shaping the very structures they call home. This cosmic partnership between black holes and galaxies hinges on a clear growth path, but a glaring gap in the evidence threatens to break the chain. We have observed small black holes, the remnants of massive stars, weighing up to around 100 times the mass of our Sun. And we know supermassive black holes, the giants at galactic centers, weighing millions to billions of solar masses. The baffling mystery is the profound emptiness in between. Where are all the intermediate mass black holes? This missing link, this vast desert in the black hole mass spectrum, represents a critical unsolved puzzle in cosmic evolution. Finding these middleweight black holes is absolutely essential. They are the hypothesized stepping stones, the missing rungs on the ladder that would connect the small stellar mass black holes to the supermassive ones. If supermassive black holes grew from tiny seeds by relentlessly swallowing gas and merging with other black holes, they must have passed through this intermediate stage. The fact that we see so few of them suggests that either this growth process is incredibly efficient and rapid, leaving few behind, or that our entire model of how these giants form is fundamentally flawed. Perhaps supermassive black holes were simply born big, bypassing the intermediate stage altogether. The challenge in finding them is one of scale and environment. An intermediate mass black hole weighing, say, a few thousand solar masses would not have the same brilliant, disruptive presence as a supermassive black hole powering a quasar. If it sits in a sparse region with little gas to feed on, it could be virtually dark and silent. So how do you hunt for a faint, dark object in the vastness of space? Astronomers have become cosmic detectives looking for subtle gravitational clues. One promising method is to watch the motion of stars within dense globular clusters, spherical swarms of millions of stars that orbit galaxies like distant satellites. By precisely tracking how stars whip around a cluster's core, scientists can detect the gravitational pull of an unseen central mass. In several clusters like Omega Centauri and a cluster named G1, the stellar motions strongly suggest the presence of a dark central object weighing thousands of solar masses, a prime candidate for an intermediate black hole. Another telltale sign comes from a different kind of flash. When a stray star ventures too close to any black hole, the immense tidal forces can rip it apart in a spectacular event called a tidal disruption event. The stellar debris forms a temporary bright accretion disk as it falls in. The characteristics of the light emitted, its brightness and how it fades over time can reveal the mass of the central black hole. A few of these events have shown signatures consistent with an intermediate mass black hole as the culprit. Then there is the evidence from gravitational waves. When two black holes spiral inward and merge, they send ripples through spacetime. The LIGO and Virgo observatories have detected waves from many stellar mass black hole collisions. The hope is to eventually catch the unique, lower-frequency rumble of a merger between two intermediate mass black holes, which would be the ultimate confirmation of their existence. Each candidate discovery is a piece of the puzzle. If confirmed, these middleweight black holes would reveal the pathways of cosmic growth, showing us how the universe builds its largest structures from smaller pieces. Their very scarcity might tell a story of a violent youth where frequent mergers quickly propelled them into the supermassive class. Or perhaps they are hiding in plain sight, in environments we have only just begun to explore. Solving the mystery of the mass gap is not just about finding a missing object. It is about mapping the entire life story of the most powerful entities in the cosmos. The silent growth of these cosmic giants should leave a trace, a faint vibration echoing across the cosmos. Every merger between supermassive black holes, a collision of unimaginable power, sends ripples through the very fabric of spacetime. These are gravitational waves, but not the sharp chirps detected from stellar mass black holes. Instead, scientists have been hunting for something far more subtle, a collective hum from all the merging supermassive black holes throughout the entire history of the universe. This is the gravitational wave background, a stochastic or random sea of vibrations. It is the combined whisper of countless cosmic dances, each one shifting the structure of reality by a minuscule amount. Detecting this background has been one of the most daunting challenges in modern astrophysics. The waves from supermassive black hole binaries are incredibly long, with wavelengths that can span light years, and their oscillations are so slow that a single wave can take years or even decades to pass by. You cannot build an instrument on Earth large enough to catch them, so astronomers turn the entire galaxy into a detector using pulsars. These are the lighthouses of the cosmos, rapidly spinning neutron stars that emit beams of radio waves with metronomic precision. By monitoring an array of these pulsars across the Milky Way for over a decade, scientists can look for tiny, correlated shifts in their rhythmic pulses. The idea is breathtakingly simple. As a gravitational wave passes between us and a pulsar, it minutely stretches and squeezes the space, causing the pulse to arrive a little early or a little late. By comparing the timing of dozens of these cosmic clocks, researchers can look for a common pattern, a signature of the gravitational wave background washing over our galaxy. For years, the data showed only silence, but recently, several international collaborations announced a monumental breakthrough. They have found a strong signal consistent with this background hum. The universe, it seems, is ringing with the echoes of black holes. This is not a single note, but a choir, a cacophony of low-frequency rumbles. What does this cosmic hum tell us? First, it suggests that supermassive black hole binaries are common, and that they do eventually merge, solving a long-standing puzzle about their fate. The amplitude of the hum points to a population of incredibly massive black holes, perhaps heavier than we expected, merging frequently throughout cosmic time. But there is a twist. The signal appears to be louder than some predictions. This could mean that the universe was a more violent place in the past, filled with more frequent and more massive black hole mergers than our models suggested. Or it might be hinting at something even more exotic. While supermassive black holes are the prime suspects, other, more speculative phenomena could be contributing to this background, such as cosmic strings from the early universe or even processes from the Big Bang itself. The detection of this hum is not the end of the mystery, it is the beginning. As the pulsar timing arrays gather more data, they will begin to resolve individual frequencies within the noise, potentially picking out the song of a single, nearby supermassive black hole binary. We are now listening to the universe's deepest vibrations, a low-frequency soundtrack written by the most powerful objects in existence, telling a story of growth and collision on a truly cosmic scale. That cosmic hum of merging giants is written in the language of space-time itself, but the silent portraits we have captured hold mysteries of their own. The first ever images of a black hole's shadow, taken by the Event Horizon Telescope, were celebrated as a triumph of human ingenuity, confirming the existence of these cosmic monsters. Yet, for all their clarity, these pictures are filled with puzzling anomalies that challenge our expectations. The bright ring of light surrounding the dark central shadow in both Messier 87's black hole and our own Sagittarius A star is not a uniform halo. It is strikingly lopsided, a brilliant crescent on one side and a much dimmer glow on the other. This asymmetry is a direct clue to the chaotic environment just outside the event horizon. The light comes from superheated gas whipping around the black hole at nearly the speed of light. Due to a relativistic effect called Doppler beaming, the material moving toward us appears intensely bright, while the material moving away from us is dimmed into near invisibility. The specific pattern of this brightness, however, is not perfectly symmetrical, telling us that the accretion flow is not a simple, smooth disk but a turbulent, messy whirlpool with complex internal motions. Perhaps even more intriguing is the alignment of the powerful jet erupting from Messier 87. The base of that colossal beam appears to be connected to the bright part of the ring, but not in the way some models predicted. This suggests that the magnetic fields threading the black hole and its disk are not just powerful, but incredibly organized, acting like a rigid funnel that directs energy and matter away from the poles. The exact mechanism that creates and sustains this ordered magnetic field structure in such a violent, chaotic place is a major open question. The magnetic fields may be so strong that they actually push back on the infalling matter, controlling its flow and even helping to launch the jet itself. These anomalies are not flaws in the image, they are cosmic breadcrumbs leading us toward a deeper understanding. They force us to ask whether our simulations of accretion physics are complete. Could the magnetic fields be so dominant that they change the fundamental way matter spirals inward? The images of Sagittarius, a star, add another layer to the puzzle. It shows a similar shadow, but its brightness ring seems to change and flicker more rapidly than the one in Messier 87. This makes perfect sense when you consider the scale. Our galaxy's black hole is much smaller, so the material orbits it in a matter of minutes rather than days, creating a dynamic, ever-shifting portrait that is incredibly difficult to capture. Future observations will be key to unraveling these mysteries. The Event Horizon Telescope is constantly adding new telescopes to its network, creating a virtual dish with even sharper vision. With this improved resolution, we will not just see a brighter crescent, we will be able to map the magnetic field lines directly and track individual clumps of gas as they orbit the black hole. We might even capture a movie of the accretion flow in real time, watching as magnetic fields snap and reconnect, releasing enormous bursts of energy. These are not static images, they are the first frames of a cosmic film, one that promises to reveal the fundamental forces at work just outside the point of no return. This brilliant, lopsided ring of light hides a theoretical war over what truly happens at the event horizon. The peaceful no-drama crossing predicted by Einstein is now challenged by one of the most radical ideas in modern physics, the firewall hypothesis. This proposal suggests that the event horizon is not a smooth, empty gateway, but a searing wall of high-energy radiation that would instantly incinerate any object attempting to cross it. The motivation for this shocking idea is to solve the information paradox. Remember, quantum mechanics insists that information cannot be lost, but Hawking radiation seemed to erase it. The firewall emerges from a thought experiment about what happens to this information. If it is to be preserved and eventually radiated back out, it requires a drastic transfer of energy right at the horizon. This process, proponents argue, would necessarily create an immense barrier, a firewall that violently breaks the entanglement between particles, releasing the energy required to encode the information. In this view, the event horizon is not a tranquil boundary but the most energetic place in the universe. This immediately creates a monumental conflict. The firewall directly contradicts the core principle of general relativity, which states that a free-falling observer should notice nothing unusual when crossing the horizon. You cannot have both a placid, empty space and a blazing wall of fire. It is a fundamental contradiction between our two most successful theories of physics. This has split the theoretical physics community into two camps. Supporters of the firewall argue that Einstein's principle of equivalence, which underpins the no-drama idea, must break down at the quantum level near the horizon. They see the firewall as a necessary, if shocking, consequence of taking quantum mechanics seriously. The preservation of information is so sacred a law that it forces a radical reimagining of the black hole structure. Opponents, however, see the firewall as a sign that we have made a grave error somewhere in our reasoning. They argue it is a paradox in itself, an absurd outcome that points to a flaw in our understanding of how quantum entanglement and gravity interact. They are searching for a more subtle resolution, perhaps where the information is encoded without the need for such a violent event. The stakes in this debate could not be higher. If firewalls are real, then black holes are not the gentle giants of relativity but brutal cosmic shredders, fundamentally changing our concept of what happens to matter that falls in. It would mean that our classical picture of space-time breaks down completely at the horizon, not just at the singularity. If firewalls are not real, then we must find another, equally profound way to save information without violating relativity's core tenets. This is not just an academic dispute, it is a battle for the soul of physics, forcing us to ask which of our fundamental principles must be sacrificed to create a complete picture of reality. The Event Horizon Telescope cannot see a firewall directly, but its detailed maps of the magnetic fields and plasma near the boundary provide crucial data. Any model, including the firewall, must be able to explain the complex dynamic environment we are now observing for the first time. The resolution to this fiery debate will likely come from a theory we do not yet have, one that finally unites the quantum world with the force of gravity. That fiery debate over the event horizon forces us to confront a discovery that is equally strange: a deep and mysterious link between the coldest objects in the universe and the science of heat. Black holes, it turns, appear to obey the laws of thermodynamics. This seems impossible at first. Thermodynamics is the study of heat, energy, and entropy, the measure of disorder in a system. A burning log has high entropy, its atoms arranged in a chaotic, random state. A black hole, defined by just 3 numbers, was thought to be the most ordered, simplest object imaginable. It should have had nearly 0 entropy, yet in the 1970s, a young physicist named Jacob Bekenstein made a radical proposal. He argued that a black hole must have entropy and a tremendous amount of it. His reasoning was brilliant. If you were to throw a box of hot, high-entropy gas into a black hole, the total entropy of the universe would appear to decrease, violating the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease. Bekenstein realized the law could be saved if the black hole itself gained an enormous amount of entropy to compensate for the loss of the gas. The entropy of a black hole, he calculated, is proportional to the area of its event horizon. This was a completely new idea, that information could be related to a surface area, not a volume. Stephen Hawking was initially skeptical, but his own work on quantum effects led him to a stunning conclusion that cemented the connection. He discovered that black holes are not completely black. They emit a faint glow of particles, now known as Hawking radiation, and this radiation has a perfect thermal spectrum, meaning it has a specific temperature. A black hole has a temperature. This is the Bekenstein-Hawking entropy, a cornerstone of modern physics. The formula is deceptively simple. The entropy is 1/4 of the event horizon's area, measured in tiny units called Planck areas. For a stellar mass black hole, this number is astronomically huge, around 10 to the power of 78. That is a 1 followed by 78 zeros. This number represents the number of microscopic quantum states, the hidden internal configurations that correspond to the black hole's smooth, featureless exterior. It is the number of ways the black hole could have been made from all the different stars, planets, and dust that fell in. The information is not gone, it is stored on the horizon, and the entropy is the log of that immense number of possibilities. This is why the information paradox is so critical, because thermodynamics now demands that the information must be preserved. The implications ripple across all of physics. It suggests that gravity, described by general relativity, is not a fundamental force but an emergent phenomenon, much like temperature emerges from the random motion of molecules. We do not feel the jostling of individual atoms as heat, we feel it as a single collective property. In the same way, space-time and gravity may emerge from a vast number of underlying quantum bits of information entangled with each other. The event horizon is like a holographic screen, and the 3-dimensional space we experience with its force of gravity is a projection of the information encoded on that 2-dimensional surface. This connection between black hole thermodynamics and information theory is a direct bridge to a theory of quantum gravity. It provides a crucial test. Any candidate theory, be it string theory or loop quantum gravity, must be able to derive the Bekenstein-Hawking formula from first principles to explain where those 10 to the 78 microstates actually lie. The search for these fundamental degrees of freedom is one of the most active areas in theoretical physics. We are learning that the universe might be fundamentally informational at its core, and the mysterious thermodynamics of black holes is our most profound clue. If a black hole is a cosmic drain from which nothing can escape, what would its opposite look like? The equations of general relativity, the very same math that predicts black holes, also permit the existence of their theoretical mirror image, the white hole. A white hole would be a region of space-time that nothing can enter, a cosmic fountain perpetually spewing out matter and energy from a singular point of origin. Where a black hole's event horizon is a one-way door inward, a white hole's horizon would be a one-way door outward, eternally repelling any matter or light that tries to cross in. This leads to a breathtaking, though entirely speculative, possibility. Could a black hole and a white hole be connected, forming a tunnel through the fabric of the cosmos? This theoretical structure is known as an Einstein-Rosen bridge, or more popularly, a wormhole. In this vision, the crushing singularity at the heart of a black hole is replaced by a throat, a tunnel that connects to a white hole in another time or place. The infalling matter would not be crushed into oblivion, but would instead be ejected through the white hole exit into a different universe or a distant part of our own. It is the ultimate cosmic shortcut and the ultimate escape route. So why do we see no evidence of these brilliant fountains in our sky? The problem is one of stability and physics. General relativity allows for the math of wormholes, but it also predicts they would be catastrophically unstable. The tunnel or throat of a wormhole would be held open by a form of matter with negative energy density, often called exotic matter. This is not antimatter, which has positive energy, but something truly strange, a substance that exerts negative pressure, effectively pushing space-time apart rather than pulling it together. While tiny amounts of negative energy can be created in lab experiments through quantum effects, the amount needed to stabilize a wormhole traversable by even a single atom is astronomical and may be physically impossible. Without this exotic scaffolding, the wormhole would snap shut the instant it formed, faster than the speed of light, making passage impossible. This is why white holes and traversable wormholes remain firmly in the realm of theoretical speculation. Yet, the idea is so compelling that physicists continue to explore it from new angles. One fascinating modern hypothesis suggests that the Big Bang itself was a white hole event, the ultimate eruption of space-time and energy from a singular point. Another, even more radical idea proposes that when a black hole dies through Hawking radiation, it does not vanish but transforms into a white hole, effectively reopening and spitting out all the information it ever consumed over billions of years. What would we see if we witnessed such an event? A white hole eruption would be a titanic, one-time burst of energy across the entire electromagnetic spectrum, a flash without an apparent cause that defies our understanding of cause and effect. Astronomers have occasionally detected mysterious, powerful explosions in the distant universe, and while they almost certainly have more conventional explanations, the remote possibility that we might one day see the death flash of a black hole, a white hole being born, keeps this incredible dream alive in the minds of theorists. It is a reminder that our universe, for all its apparent rules, may still hold exits where we see only endpoints. These theoretical escape routes challenge our most basic notions of causality, but an even more radical possibility threatens to shatter them completely. What if the singularity, that point of infinite density, was not hidden safely behind an event horizon? This is the terrifying prospect of the naked singularity, a cosmic anomaly stripped of its protective shield and exposed for the entire universe to see. According to Einstein's equations, such a thing is mathematically possible under certain extreme conditions. Imagine a black hole spinning at the absolute maximum rate, its centrifugal forces becoming so powerful that they counteract the immense inward pull of gravity. In this scenario, the event horizon could theoretically be torn apart, leaving the raw, naked singularity at the core exposed. The universe, however, seems to have a built-in protection against such chaos. Most physicists strongly believe in a principle called cosmic censorship, a cosmic rule that forbids naked singularities from forming. The idea is that nature abhors a paradox, and it will always wrap a singularity in an event horizon to hide it from view, preserving the predictability of the universe outside. It is as if the cosmos has its own set of sensors, ensuring that the infinitely weird physics at the center of a collapse remains a private affair, locked away forever. But what if this rule is not absolute? Are there cracks in cosmic censorship? Some theoretical models suggest that if a black hole forms from an perfectly asymmetric, non-spherical collapse, or if it consumes an exotic form of matter, a naked singularity could momentarily flash into existence before settling down. The implications of such an object being real are staggering. Without an event horizon, the laws of physics as we know them would break down in plain sight. The predictable flow of cause and effect could completely unravel. Gravity could become so twisted near a naked singularity that it creates closed time-like curves, theoretical pathways that loop back on themselves. This would open the door to time travel, not as science fiction, but as a terrifying physical possibility. You could potentially travel back in time and encounter your past self, creating paradoxes that defy logic. The very foundation of predictability, which all of science relies upon, would be destroyed. If we could observe a naked singularity, we would be peering directly into a region where density and curvature are infinite, a place where general relativity gives up and quantum gravity must take over. It would be our first direct window into the theory of everything. For now, naked singularities remain a mathematical ghost, a warning of what could happen if the universe's deepest secrets were left unguarded. Their hypothetical existence forces us to ask whether the cosmos is fundamentally orderly, or if true chaos is merely waiting for the right conditions to reveal itself. That staggering number, 10 to the 78, represents the universe's ultimate accounting problem. What are the microscopic components that give rise to a black hole's immense entropy? We know the total, but we cannot find the ledger. This is the profound challenge of identifying the black hole's fundamental degrees of freedom, the tiny quantum units whose vast number of possible configurations equals that astronomical figure for entropy. Solving this is not just an academic exercise, it is widely seen as the most direct path to a theory of quantum gravity. The leading candidates for this ultimate theory offer wildly different pictures of this hidden microstructure. String theory, for instance, proposes that the fundamental entities are not particles but incredibly tiny, vibrating loops of string. In certain specific, highly symmetric black hole setups, string theorists have successfully counted the number of ways these strings can vibrate and tangle together. The result matched the Bekenstein-Hawking entropy formula perfectly, a monumental triumph that fueled the entire field. This suggests the entropy comes from the different vibrational states of these strings, the countless ways they can store energy and information on the surface of the event horizon. Loop quantum gravity takes a different approach. It suggests that space-time itself is not smooth and continuous, but is woven from a fabric of finite, discrete loops. In this view, the event horizon is like a tapestry made from these individual threads. The entropy then comes from the different ways these quantum loops can pierce the horizon, creating a unique pattern of intersections for every possible configuration of matter that fell in. Each puncture in the fabric of space-time represents a tiny bit of area, and the different combinations of these punctures account for the huge number of microstates. Then there is the holographic principle, which argues that the degrees of freedom are not within the black hole's volume at all. They live on its boundary. Imagine a three-dimensional room with all its furniture and people being perfectly described by a two-dimensional painting on the wall. The entropy is not a measure of disorder inside the black hole, but of the information encoded on its two-dimensional surface. The microscopic details are pixels on that cosmic screen, and counting the number of ways to arrange those pixels gives us the entropy. Each of these approaches is a compelling vision of reality, yet each faces its own hurdles. The string theory calculation works beautifully for idealized theoretical black holes, but can it be generalized to all black holes, including the messy, spinning giants we see in nature? Loop quantum gravity provides a geometric origin for entropy, but can it fully recover the precise 1/4 of the area law without additional assumptions? The holographic principle is a radical shift in our understanding of space itself, but what is the actual physical mechanism that projects the interior onto the surface? The reason this mystery is so crucial is that any viable theory of quantum gravity must pass this test. It must be able to start from its fundamental quantum postulates and derive the Bekenstein-Hawking formula. It is the universe's final exam. If your theory cannot account for where those 10 to the 78 microstates lie, it cannot be a complete description of reality. This search is forcing us to ask what space and time truly are. Are they emergent, collective phenomena that arise from a vast network of entangled quantum bits? Is gravity itself not a fundamental force, but a thermodynamic consequence, like the pressure of a gas emerging from the random motion of molecules? The black hole is the simplest object in the universe, defined by only a few numbers, yet it contains the deepest secret of all. Its silence holds the key to the quantum code of spacetime. The silent accounting of 10 to the 78 microstates is a ledger written in gravity, and that gravity can scream. When two supermassive black holes, the anchors of merged galaxies, finally spiral together, they unleash a torrent of gravitational waves, ripples in spacetime that carry away immense energy and momentum. This cosmic dance can have a violent finale, one that might see the newborn black hole kicked out of its galactic home at millions of miles per hour. This is the mystery of black hole recoil, a gravitational slingshot of unimaginable power. The key to this incredible phenomenon lies in the asymmetry of the merger. If the two black holes are identical in mass and spinning at the same rate and orientation, the gravitational waves they emit are symmetrical, and the final black hole settles neatly at the center of the new galaxy. But nature is rarely so perfect. More often, the black holes have different masses and wildly different misaligned spins. As they whirl around each other in their final moments, they emit gravitational waves more strongly in one direction. In a final burst, this last, lopsided pulse of radiation can impart a tremendous kick to the merged black hole, a recoil that sends it rocketing through interstellar space. The velocities involved are staggering. Theoretical models suggest these kicks could reach thousands of kilometers per second, more than enough to overcome the gravitational pull of even the largest galaxies. Imagine the core of a galaxy having just undergone a titanic collision, suddenly finding itself without its central gravitational anchor. The stars would be left orbiting an empty point, a ghost at the center of the cosmic machine. Astronomers are actively hunting for these wanderers, these rogue supermassive black holes cast adrift. The evidence is subtle but compelling. We see galaxies with bright, active nuclei that are noticeably offset from their dynamical center, as if the engine powering the glow has been shoved to the side. In other cases, we find what appear to be bare quasars, brilliant beacons shining from the emptiness between galaxies, with no visible host galaxy surrounding them. These could be black holes that received such a powerful kick they escaped entirely, trailing a shroud of glowing gas as their final trophy. The search also leads to tidal disruption events, the violent shredding of a star. If we see one of these flashes occurring far from the center of a galaxy, it might signal a black hole passing through the galactic outskirts, a nomad briefly lighting its campfire on a long, dark journey. The existence of these wanderers reveals a violent history of galaxy mergers. Every recoiling black hole is a fossil record of a past collision, a time when two galaxies became one, and their central monsters fought a gravitational duel with the loser or sometimes the winner being thrown clear. This raises a profound question about the growth of the largest black holes. If the most massive ones are frequently ejected during mergers, how did they ever get so big? It is possible that the largest giants form in environments where kicks are less effective, or that they grow primarily by steadily sucking in gas rather than through violent collisions. The detection of gravitational waves from supermassive black hole mergers by future space-based observatories will give us a direct measure of these kicks. By reading the specific patterns in the waves, we will be able to calculate the exact velocity and direction of the final black hole's recoil. We will witness for the first time the moment a galaxy loses its heart, watching as a gravitational titan is sent flying into the void, a permanent exile written in the waves of spacetime itself. These recoiling giants reveal that a black hole is far more than its mass alone. Its silent, relentless rotation holds a history written in gravity, a record of everything it has ever consumed. Measuring the spin of a supermassive black hole, however, is one of the most difficult tasks in all of astronomy. We are trying to gauge the rotation of an object that emits no light from a distance of millions of light years, an object defined by its ability to hide. Why is this spin so important? Because it tells two stories. First, it reveals the black hole's life story. Did it grow steadily by sucking in gas from a single, orderly disk, a process that spins it up like a twirling ice skater pulling in their arms? Or did it grow through chaotic mergers with other black holes, collisions that can spin it up, slow it down, or even send it tumbling end over end? The spin is a fossil of its dietary past. Second, and more dramatically, spin is the likely power source for those universe-spanning relativistic jets. A rapidly spinning black hole stores an immense reservoir of rotational energy, which can be tapped by magnetic fields rooted in its accretion disk, launching matter into the void at near light speed. A dormant, non-spinning black hole could never power such a spectacle. So how do we measure this invisible rotation? Astronomers have developed several ingenious yet conflicting methods. One primary technique uses X-ray spectroscopy. When a black hole feeds from a hot accretion disk, the inner edge of that disk gets so close that it is dragged by the black hole's spin, an effect known as frame dragging. The faster the spin, the closer this inner edge can get. Atoms like iron in this searing plasma emit X-rays at very specific energies. As this light climbs out of the black hole's immense gravitational grip, its energy is shifted or redshifted. By studying the precise distortion of this X-ray signal, we can map how deep the disk goes and therefore infer the black hole's spin. But this method has its pitfalls. It assumes the accretion disk is smooth and well-behaved, which it often is not. Clumps of material, magnetic turbulence, or overlapping winds can contaminate the signal, leading to different spin estimates from different observations of the same black hole. Another method observes the black hole's shadow. The Event Horizon Telescope's image of the ring of light is not perfectly circular if the black hole is spinning rapidly. The spin squashes the shadow, making it appear slightly flattened on one side. Measuring this distortion provides a direct geometric measure of spin, independent of the messy physics of the accretion disk. Yet this too is incredibly challenging, requiring even sharper images than we currently possess. Then there is the future promise of gravitational waves. When two black holes merge, the gravitational wave signal carries an unmistakable imprint of their spins. For supermassive black holes, future space-based observatories will detect these low-frequency waves, giving us a direct readout of spin from the moment of collision. Each of these methods is like a different doctor examining the same patient with different instruments, and they do not always agree. One might suggest a black hole is spinning at nearly the maximum possible rate, while another indicates a more modest rotation. These conflicts are not failures, they are clues. They tell us that our models of the extreme environment near the event horizon are incomplete. we are learning that the space around a spinning black hole is a dynamic, violent place where magnetic fields and plasma interact in ways we are only beginning to understand. Resolving the spin mystery is not just about getting a number, it is about learning to read the complex life story of the universe's most powerful engines. That theoretical hair might not be a metaphor after all. The classic no-hair theorem is a beautiful result of pure general relativity, but our universe is not purely classical. It runs on quantum mechanics, and when you apply even the tiniest quantum corrections to Einstein's equations, something remarkable happens. The black hole is no longer perfectly bald. It sprouts what physicists are calling quantum hair. This is not hair you could see, but incredibly subtle imprints in the gravitational field, permanent distortions that linger on the event horizon. These imprints are a direct record of the quantum properties of everything that ever fell inside. Think of it like a phantom limb. Even after an amputation, the brain can sometimes still feel the presence of the missing arm or leg. Quantum hair is the black hole's phantom memory, a gravitational echo of every star and planet it has consumed. The mathematical evidence for this is growing. Researchers have shown that when you model matter falling into a black hole using quantum field theory, the gravitational field outside does not settle back into a perfect, featureless state. It retains a faint but permanent deformation, a unique signature determined by the internal composition of what fell in. A black hole that ate a proton would have a slightly different quantum hair than one that ate a neutron, even if their total mass, charge, and spin were identical. This is a direct challenge to the decades-old dogma that all information is lost. What does this mean for the information paradox? It offers an elegant escape. If quantum hair exists, then the information about what fell in is never truly trapped behind the horizon. It is encoded right there on the surface in these infinitesimal gravitational twists. When Hawking radiation is emitted, it can interact with this quantum hair, subtly imprinting the information into the radiation that escapes. The information is not destroyed, it is slowly and meticulously leaked back into the universe, one quantum particle at a time. The paradox dissolves because the fundamental premise was wrong. Black holes are not the simple, information-erasing objects we thought they were. The challenge now is moving from mathematical elegance to observational proof. How could we possibly detect such a faint signal? The most promising test lies in the echoes of black hole collisions. When two black holes merge, they vibrate like a struck bell before settling down. According to the classical no-hair theorem, this ring down should be clean and simple, described by only a few tones that quickly fade. But if quantum hair is present, it would make the event horizon a more complex structure. The ring down would contain faint secondary echoes, like a bell with a complex internal texture producing a richer, more lingering sound. Our current gravitational wave detectors are not yet sensitive enough to pick out these whispers, but the next generation of observatories might be. Another possibility involves watching stars orbit our galaxy's own supermassive black hole, Sagittarius, a star. If it has quantum hair, its gravitational field would deviate by a minuscule amount from the perfect prediction of general relativity. By tracking the orbits of stars like S2 with extreme precision over many years, we might one day see a slight, unexplained wobble, a tiny nudge caused by the hidden information etched into the black hole's surface. Finding quantum hair would be more than just solving a 50-year-old puzzle. It would fundamentally change our view of reality. It would mean that black holes are not cosmic dead ends, but the universe's most secure vaults safeguarding every secret they have ever swallowed. The quantum hairs on a modern black hole are subtle whispers, but their theoretical ancestors would have been cosmic shouts. Scattered throughout the universe could be a hidden population of primordial black holes, ancient relics forged not from dying stars, but from the raw, dense chaos of the Big Bang's first moments. These would be the universe's first black holes, and their existence would rewrite our understanding of cosmic evolution. the formation mechanism is radically different from anything we see today. In the incredibly hot, dense soup of the early universe, tiny regions could have experienced extreme pressure fluctuations. Think of it like a boiling pot of water, where random bubbles of higher density form and collapse. In that primordial soup, some of these density peaks could have been so intense that their own gravity caused them to directly collapse, bypassing the need for a star entirely. The size of these first black holes would depend entirely on when they formed. A patch collapsing when the universe was just 1 second old could create a black hole with the mass of a planet. One forming even earlier, a mere fraction of a second after the beginning, could be as light as a mountain yet smaller than an atom. This wide range of possible masses is what makes them so compelling and so elusive. They could be almost anywhere from the mass of an asteroid to thousands of suns, silently drifting through the cosmos for billions of years. Why has finding them been so difficult? Primordial black holes would be naturally dark and incredibly compact. A black hole with the mass of Earth would be only the size of a peanut, making it nearly impossible to see directly unless it happens to feed on a passing wisp of gas. For decades, the search has relied on clever indirect methods. One of the most productive is gravitational microlensing. When one of these invisible, compact objects passes directly between us and a distant star, its gravity acts as a lens, bending the star's light and causing it to temporarily brighten. Astronomers have scanned millions of stars for years, looking for these characteristic flashes. The results have been puzzling. They have not found the vast numbers of planet-mass primordial black holes that will be needed to account for all dark matter, but they have detected a surprising number of unexpected, isolated compact objects. This suggests that while they may not be the sole answer to the dark matter puzzle, a hidden population of these ancient objects might still be lurking in the dark. The most exciting new tool in this hunt is gravitational wave astronomy. When two primordial black holes spiral together and merge, they create ripples in spacetime. The LIGO and Virgo observatories have detected many black hole mergers, and a significant number of them fall into a mass range that is difficult to explain through standard stellar collapse. These are black holes weighing between roughly 50 and 100 solar masses. How do you get a star that massive? It is a challenge for astrophysicists. But if these are primordial black holes, their mass is not a mystery. It is a direct fossil of the conditions in the early universe. Every merger we detect in this strange mass range is a potential candidate, a clue that we are listening to the echoes of the cosmos's birth. Finding a definitive primordial black hole would be like discovering a living dinosaur. It would be a direct window into the most extreme physics of the Big Bang, confirming that the infant universe was a far wilder and more violent place than we ever imagined. It would mean that drifting unseen through the galaxy are black holes that witnessed the very first light, ancient monuments to the moment of creation itself. The serene glow of a black hole's accretion disk is a cosmic lie. Far from a placid, orderly whirlpool, this region is a scene of violent chaos, subject to wild and unpredictable outbursts that defy our best simulations. We label this as Mystery 21, the bewildering instabilities of the accretion disk. These are not minor flickers, but dramatic transformations in brightness and structure that can see a black hole's output surge by a factor of 100 in mere hours. Why does matter, on the very brink of oblivion, behave with such erratic fury? The root of the chaos lies in the complex physics of how the disk stores and transports energy. One primary culprit is a thermal instability. Imagine the disk as a vast, rotating highway for gas. Under normal conditions, this gas radiates away heat as fast as it generates it through friction, maintaining a stable temperature. But past a certain critical density and temperature, the gas can no longer cool itself efficiently. It's like a car engine overheating because the radiator fails. The trapped thermal energy causes a runaway heating event, making the gas suddenly much hotter and brighter. This can transform a dim, cool disk into a brilliantly shining one in an astronomical instant. Another powerful mechanism involves the buildup and sudden release of magnetic energy. The disk is threaded with immensely powerful magnetic fields, which get twisted and wound up by the differential rotation, the inner parts orbiting much faster than the outer parts. This is like twisting a rubber band tighter and tighter. Eventually, the tension becomes too great, and the magnetic field lines snap and reconnect in a colossal short circuit. This magnetic reconnection event unleashes a torrent of energy, heating the plasma to incredible temperatures and launching violent flares that we can see across the electromagnetic spectrum, from radio waves to X-rays. These instabilities are more than just a light show. They are a direct window into the black hole's feeding habits. A stable, predictable disk suggests a black hole enjoying a steady, orderly diet. A wildly variable one, flashing and flaring, tells us the black hole is eating in messy, chaotic gulps. The gas might be falling in clumps, or the entire disk might be undergoing global oscillations, sloshing around like water in a giant cosmic bowl. Our models often fail because we are trying to simulate a system of mind-boggling complexity with limited computing power. We must account for general relativity, magnetohydrodynamics, radiation transport, and particle physics all at once, in an environment where gravity is supreme and space-time itself is dragged into a whirl. The sheer scale makes it impossible to simulate every atom, forcing us to use approximations that inevitably miss some of the turbulence's fine detail. This is why every new observation from telescopes like the Chandra X-ray Observatory or the Event Horizon Telescope is so vital. When we see a black hole like Sagittarius, a star, suddenly flare up, becoming hundreds of times brighter for a short while, we are witnessing these instabilities in real time. By comparing these outbursts to our simulations, we slowly refine our understanding of the fundamental forces at play. Cracking the code of accretion disk instabilities does more than explain a black hole's mood swings. It reveals the intricate mechanics of how the universe's most efficient engines convert matter into pure energy, one violent, unpredictable gulp at a time. These violent instabilities in a black hole's feeding process hint at something even more profound hidden within its core. A new and radical theory suggests that the ultimate secret of a black hole is not just what it destroys, but what it creates, and that this creation might be driving the entire cosmos apart. This is the speculative but astounding link between black holes and dark energy. Dark energy is the name we give to the mysterious force causing the expansion of our universe to accelerate, a discovery that earned a Nobel Prize. We know it exists because of its overwhelming effect on cosmic evolution, yet its origin remains one of the greatest puzzles in all of science. For decades, dark energy and black holes were treated as entirely separate phenomena, one governing the vast cosmos and the other ruling tiny, violent points within it. But what if they are two sides of the same cosmic coin? A provocative idea has emerged from the study of black hole thermodynamics. Remember the Bekenstein-Hawking entropy, the concept that a black hole's entropy is proportional to its event horizon's area. When you apply the equations of general relativity to this idea, something remarkable appears in the math. The interior of a black hole seems to contain a form of energy with negative pressure, an energy inherent to the vacuum of space itself. This is precisely the kind of energy that, if it existed on cosmic scales, would cause a repulsive gravitational effect, accelerating the universe's expansion. In this theory, black holes are not just consumers of matter, they are cosmic batteries storing vacuum energy. As a black hole grows, its interior volume increases, and so does the amount of this repulsive vacuum energy it contains. Over the eons, as supermassive black holes in galactic centers have grown to immense sizes, the collective contribution of their internal vacuum energy could have become the dominant force in the universe, manifesting as what we call dark energy. The theory elegantly suggests that the accelerating expansion of the cosmos is not driven by some mysterious field spread evenly through space, but is a cumulative effect of the vacuum energy locked inside every supermassive black hole. This provides a potential solution to the cosmological constant problem, a major headache in physics which asks why the calculated energy of the vacuum is so wildly different from the observed value of dark energy. If dark energy is tied to black holes, its value is not a fixed property of empty space, but an evolving consequence of the total number and mass of black holes in the universe. It is dynamic, not constant, so where is the evidence for such a mind-bending connection? Astronomers have begun looking at the growth of supermassive black holes over cosmic time. They are comparing the total energy density of dark energy today with the cumulative mass gained by all supermassive black holes throughout history. Early results suggest the numbers are intriguingly similar, a tantalizing clue that demands further investigation. Yet the theory faces immense challenges. The biggest question is one of coupling. How does the vacuum energy sequestered inside a black hole behind its event horizon manage to affect the entire universe outside? How does the private energy of these isolated objects become a public force driving cosmic expansion? Solving this requires a new understanding of how gravity works on the largest scales, perhaps one where the universe's global properties are deeply entangled with the local properties of its most extreme objects. This idea bridges the largest and smallest scales in physics, connecting the fate of the entire cosmos to the mysterious hearts of black holes. If it is correct, then the supermassive black hole at the center of our Milky Way is not just a silent giant, it is a tiny engine of cosmic repulsion, its hidden energy contributing to the grand, accelerating flight of the galaxies. That fiery debate over the information paradox has given rise to a concept so strange it seems to belong in science fiction. Two of Einstein's most puzzling ideas, once thought to be entirely separate, might be one and the same. This is the ER equals EPR conjecture, a proposal that suggests quantum entanglement and wormholes are two sides of the same cosmic coin. The letters come from two classic physics papers, ER for Einstein-Rosen bridges, which are wormholes, and EPR for Einstein-Podolsky-Rosen, which describes the spooky action at a distance of quantum entanglement. The radical idea is that every pair of entangled particles, those ghostly twins connected across any distance, might be linked by a microscopic wormhole, a tiny bridge in the fabric of spacetime. If this is true, then the fabric of our universe is not smooth and continuous, but is instead woven together by an unimaginably complex network of these quantum threads, a cosmic tapestry of hidden connections. This idea completely reframes the black hole information paradox. Imagine a particle falling into a black hole. According to standard theory, it crosses the event horizon and its information is lost. But if ER equals EPR is correct, that particle is instantly entangled with a partner particle that remains outside, the Hawking radiation. Their connection is not some mysterious signal, it is a physical bridge, a microscopic wormhole. The information describing the infalling particle never actually travels into the black hole's interior. Instead, it is instantly transmitted through this wormhole and encoded onto the Hawking radiation particle fleeing into the wider universe. The black hole, in this view, is not a prison for information but a vast, tangled knot of these wormhole connections, a gateway that preserves everything. The event horizon is not a destructive boundary but a transformative one where information is rerouted rather than erased. This provides a potential escape from the firewall paradox as well. If every infalling particle is connected to an outgoing one by a wormhole, there is no sharp, singular boundary where information gets scrambled and released in a fiery burst. The transition is smooth because the interior of the black hole is already connected to the exterior through this labyrinth of quantum bridges. You are not crossing a line into oblivion, you are stepping into a network of tunnels that lead back out. The implications of this are staggering for our understanding of reality itself. It suggests that space-time, the very stage upon which the universe plays out, is not fundamental. It emerges from something deeper, from the quantum entanglement between particles. Where there is no entanglement, there is no space. This is like realizing that the air in a room is not a primary substance, but emerges from the collective motion of countless invisible molecules. The three-dimensional world we experience could be a holographic projection from a vast, interconnected quantum system. For black holes, this means they are not the end of physics, but a window into its foundations. Their immense gravity and quantum weirdness force the hidden architecture of spacetime to reveal itself. The ER equals EPR conjecture is still purely theoretical, a map without a territory. Proving it would require a full theory of quantum gravity, the very thing it seeks to inform. Yet, it represents a monumental shift in thinking, uniting the two great pillars of modern physics, general relativity and quantum mechanics, by showing that the universe's spookiest connection might be its most fundamental glue. This controversial idea forces us to abandon our most basic intuition about location. The black hole complementarity principle makes a claim that sounds impossible, that the information about a particle falling into a black hole is both irretrievably lost inside the singularity and simultaneously perfectly preserved on the event horizon. Both stories are true, but they are true for different observers, and crucially, no single observer will ever witness the contradiction. It is a cosmic sleight of hand that redefines reality itself. For an astronaut plunging toward the horizon, their journey is smooth and uneventful. They cross the boundary without incident, carrying all their information with them into the mysterious interior. For a distant physicist watching through a telescope, the astronaut never actually crosses. They see the astronaut's image redden, freeze, and smear across the horizon, with all their information encoded in the quantum fluctuations of that surface, eventually radiated back out as Hawking radiation. The principle states that both of these wildly different descriptions are valid and complementary, much like how light can be both a particle and a wave. The contradiction only arises if we insist that a single, God's-eye view of reality exists, a perspective that quantum mechanics has always told us is forbidden. The key is that no information is ever duplicated. The same information exists in two different places, but it is forever separated by a causal horizon, ensuring that no one can ever compare the two copies and witness the paradox. This radical rethinking of locality suggests that the concept of a single, objective where breaks down under such extreme conditions. The debate surrounding complementarity is fierce. Proponents see it as the most elegant way to resolve the information paradox without invoking firewalls or violating cherished principles. It preserves the no-drama experience for the infalling observer while saving quantum mechanics for the outside universe. Critics, however, argue it is a clever trick that papers over a deeper problem. They question how information can be in two places at once without any physical mechanism to explain the transfer, seeing it as a philosophical surrender rather than a physical solution. The true power of complementarity lies in what it implies for a theory of quantum gravity. It suggests that spacetime is not the fundamental stage of the universe, but an emergent, approximate concept. Our classical notion of a single, continuous reality is a useful illusion that shatters at the event horizon, revealing a deeper, more complex quantum reality where our everyday rules of location simply do not apply. The event horizon becomes a transformative boundary where one description of reality smoothly transitions into another, a place where the universe itself performs a magic trick to preserve its own logical consistency. Even the most powerful gravitational duet in the cosmos can fall silent. After two galaxies collide, their central supermassive black holes are drawn together by gravity, sinking toward the galactic core in a cosmic dance. But this dance seems to freeze when the black holes reach a separation of about 1 parsec, a distance of roughly 3.26 light-years. This is the final parsec problem, a mysterious stalling that threatens to leave these giants in a perpetual standoff, never close enough to merge and produce the loudest gravitational waves in the universe. The core of the problem is a loss of momentum. In the vast, empty space of a galactic core, there simply is not enough matter for the black holes to interact with. They lose energy by gravitationally slinging stars away, a process known as dynamical friction. But once they clear out their immediate neighborhood of stars, this process becomes incredibly inefficient. With no more stars to eject, the black holes have no way to shed their orbital energy and spiral closer together. They are left stranded, a binary pair forever circling each other across a vast, empty gulf. So how does the universe solve this cosmic traffic jam? One solution involves a third black hole, an interloper from a previous galactic merger. This third body can gravitationally perturb the stalled binary, transferring energy and angular momentum in a chaotic three-body interaction that can kick one black hole away while driving the other two closer together, finally pushing them across the final parsec. Another possibility relies on a vast gaseous disk. If the merged galaxy retains a significant reservoir of gas, this material can form a circumbinary disk around the black hole pair. As the black holes orbit, they create spiral density waves in this gas gravitational grooves that sap their orbital energy and allow them to inch closer together over millions of years. The nature of the galaxy itself may be the key. In galaxies with steeply rising central densities, known as core galaxies, the stalling is more severe. But in galaxies with a more gradual distribution of stars, there may be a steady supply of new stars whose orbits are perturbed into the black hole's path, providing the continued friction needed for inspiral. Resolving this mystery is not just an academic exercise. It is absolutely crucial for predicting the gravitational wave signals that future space-based observatories like the Laser Interferometer Space Antenna or LISA hope to detect. If most supermassive black hole binaries stall at the final parsec, the universe will be far quieter than our models predict, with a faint gravitational wave background. But if nature has efficient mechanisms to solve this problem, then the cosmos should be ringing with the deep, low-frequency hum of countless mergers, a chorus we are poised to hear for the first time. The silence or the song will tell us which of these cosmic dances reaches its violent, universe-shaking finale. These cosmic paradoxes all point toward a single, monumental goal. Supermassive black holes are not merely astronomical objects. They are the universe's most demanding natural laboratories, forcing us to confront the final frontier in physics, the quest for a theory of quantum gravity. This is the grand challenge of uniting the realm of the immensely large, governed by Einstein's general relativity, with the realm of the vanishingly small, ruled by the bizarre laws of quantum mechanics. Each theory is spectacularly successful in its own domain, but they offer completely contradictory descriptions of reality, and this conflict becomes unavoidable at the heart of a black hole. The immense gravity warps spacetime to its breaking point, while quantum effects flicker at the horizon, creating an environment where only a unified theory can describe what is truly happening. These celestial giants are the only places in the universe where the effects of quantum gravity might be amplified to a detectable scale, offering us a chance to peek at the fundamental code of reality. The leading contenders in this quest each paint a radically different picture of a black hole's interior. String theory, for instance, proposes that the fundamental constituents of reality are not point particles, but incredibly tiny, vibrating loops of string. In this view, the terrifying singularity might be replaced by a fuzzball, a vast, tangled ball of cosmic strings that prevents the formation of a true point of infinite density. The information that falls in is not lost but becomes trapped in the complex vibrations of this quantum knot. Loop quantum gravity takes a different approach, suggesting that space-time itself is not smooth and continuous, but is woven from a fabric of finite, discrete loops. There is a smallest possible volume, a fundamental pixel of reality. This means matter collapsing into a black hole cannot be crushed to a point. Instead, it would meet a fierce quantum resistance and rebound in a cosmic bounce, potentially giving birth to an entirely new universe inside the black hole, transforming these monsters into portals. A third, less-known idea called asymptotic safety proposes that gravity behaves differently at incredibly high energies. In this scenario, the force of gravity might weaken near the center of a black hole, acting as a natural shield that prevents the singularity from ever forming. The black hole would contain a dense but finite core of exotic matter. Each of these theories makes different testable predictions. They would affect how a black hole evaporates via Hawking radiation, how it vibrates when it rings down after a collision, and what its shadow truly looks like. The precise shape of the shadow captured by the Event Horizon Telescope, the specific frequencies in the gravitational waves from a merger, and the statistics of Hawking radiation all hold subtle clues. By comparing these exquisite observations against the predictions of each theory, we are running a real-world experiment on the nature of space-time itself. What these black holes ultimately reveal is that space and time may not be fundamental. They could be emergent properties, collective illusions that arise from a deeper layer of interconnected quantum bits. The smooth, continuous stage upon which the universe plays out might be a mirage, a convenient approximation that shatters under the extreme gravity of a supermassive black hole. Unlocking their secrets is not just about understanding these dark giants. It is about reading the first lines of the cosmic code, the quantum language in which the universe was written. The dark shadow at a black hole's heart is not the only thing that bends light. The very glow surrounding it carries a hidden signature, a subtle fingerprint of polarization that reveals forces at work we cannot see directly. When the Event Horizon Telescope released its first historic images, it later unveiled a follow-up analysis, a map of the polarization in the ring of light around both Messier 87's black hole and our own Sagittarius A star. This was not just a picture of brightness, it was a portrait of magnetic fields. The patterns were startlingly complex, showing organized spiral-like structures in the searing plasma. Polarization is a property of light that tells us about the alignment of its waves. In the violent whirlpool of an accretion disk, the light emitted by superheated electrons becomes polarized as it travels through powerful magnetic fields. These fields act like cosmic combs, brushing the light waves into a preferred direction. The specific swirls and twists we see in these polarization maps are a direct trace of the magnetic field lines themselves, frozen in the act of whipping around the black hole at near light speed. This discovery immediately challenged our simulations. Many models predicted far more chaotic, turbulent magnetic fields, a messy tangle of energy. Instead, we see a surprising degree of order, especially in the regions where the powerful relativistic jets are launched. The magnetic fields appear strong, organized, and perpendicular to the disk, forming a rigid, rotating structure that can efficiently funnel material away from the black hole's poles. This provides the clearest evidence yet that magnetic fields are not just a side effect of the accretion process, they are the primary engine for jet formation. They act like the rails of a cosmic particle accelerator, directing and focusing the immense energy generated by gravity into those narrow, universe-spanning beams. The polarization also tells a story about the nature of the plasma itself. The degree of polarization is affected by the temperature and density of the electrons in the disk. By analyzing it, we can determine whether the plasma is a so-called radiatively inefficient flow, a puffed-up, tenuous soup of particles, or a thin, efficient, and bright disk. The data so far suggests a hybrid, a complex environment where different states of matter coexist in a turbulent dance. Future observations will turn this snapshot into a movie. The next goal is multi-wavelength polarization, observing the same black hole simultaneously in radio waves, infrared, and X-rays. Each wavelength probes a different layer of the accretion flow and a different population of electrons. Radio waves show us the cooler outer regions and the base of the jet. Infrared light reveals the hotter plasma closer to the event horizon. X-rays come from the most energetic processes, the flares and magnetic reconnection events right at the precipice. Combining these views will allow us to create a three-dimensional map of the magnetic field structure, from the calm outer disk all the way down to the point of no return. We will be able to watch as magnetic field lines snap and reconnect, unleashing the violent flares we see in Sagittarius, a star, and trace how energy is transported from the spinning black hole out into the jet. These polarized whispers are decoding the fundamental mechanics of how a cosmic drain becomes a cosmic fountain, revealing the invisible architecture of power that shapes the universe itself. The universe has a maximum storage capacity. This is not a limit of technology, but a fundamental law of physics, and it is written in the language of black hole thermodynamics. The Bekenstein bound is a profound concept that declares a startling truth. Any finite region of space with a finite amount of energy can only contain a finite amount of information. There is a cosmic cap on how many bits can be stored in any given volume, and that cap is determined not by the volume itself but by the area of its boundary. Think of a computer hard drive. Its storage capacity depends on its three-dimensional interior, the number of magnetic platters it can hold, but the Bekenstein bound tells us the universe operates differently. The maximum information you can fit inside any box, even an imaginary one, is proportional to the surface area of that box, not its volume. It is as if the entire three-dimensional content of a room, every book and piece of furniture, could be perfectly described by a two-dimensional painting on the wall. This is the holographic principle in its most radical form, and it emerged directly from the study of black hole entropy. A black hole is the ultimate example of this law. It has the maximum possible entropy, the maximum possible disorder for its size. The Bekenstein-Hawking formula tells us this entropy is 1/4 of the event horizon's area. That number is the total number of bits, the ones and zeros, needed to describe everything that ever fell in. The black hole's surface area is its information storage limit. This forces a staggering conclusion about our own reality. If a black hole, the densest object possible, cannot store more information than what is encoded on its boundary, then nothing in the universe can. The three-dimensional world we see and touch, with its vast volumes of space, might be a holographic projection from a two-dimensional surface at the cosmic horizon. The information required to describe every particle, every force, and every event in our cosmic neighborhood might not be contained within it, but on a distant, enclosing shell. Why would the universe be built this way? The answer may lie in the very nature of spacetime. Black hole thermodynamics suggests that gravity and the spacetime it warps is not a fundamental force. It could be an emergent phenomenon, a collective behavior that arises from something deeper. Think of temperature. A room feels warm, but that warmth is not a fundamental substance. It emerges from the frantic, random motion of countless invisible molecules. In the same way, the smooth, continuous fabric of space and time might emerge from a vast network of entangled quantum bits of information. The force we call gravity would then be a thermodynamic effect, a consequence of the universe's tendency toward disorder, much like the pressure in a gas emerges from molecular collisions. The solidity of the floor beneath your feet, the vast distance to the stars, all of it could be a grand and persistent illusion generated by underlying quantum data processing. The event horizon of a black hole is where this illusion breaks down, where the underlying quantum circuitry is exposed. The information puzzle is the key that unlocks this deeper layer of reality. The struggle to understand how data escapes a black hole is not just about saving quantum mechanics, it is about discovering the source code of the cosmos. If spacetime is emergent, then the black hole is not an object within space, but a knot in the very fabric from which space is woven, a place where the universe's hidden programming becomes visible. The universe's fundamental limit on information storage leads us to the most speculative frontier of all, a place where physics meets philosophy. Could these cosmic information processors possess a form of consciousness? This is not mainstream science, but a fringe idea that pushes the boundaries of what we consider possible. The speculation often begins with the holographic principle, the concept that our three-dimensional reality is a projection from a two-dimensional surface. If the information that constitutes our minds and experiences is just data on a cosmic screen, then perhaps consciousness itself is not a product of brains, but a fundamental property of the universe, a process occurring within the fabric of spacetime. In this radical view, a black hole, as a region of maximum information density and processing, might exhibit a primitive form of this cosmic awareness. It would not be conscious in any human sense with thoughts or feelings, but might possess a kind of intrinsic perception, a way of interacting with and responding to the information it consumes and emits. Another line of thought draws from integrated information theory, a framework that attempts to explain consciousness. This theory proposes that any system with a high degree of integrated information, where the whole is more than the sum of its parts, could possess some level of consciousness. A black hole, with its immense entropy representing countless entangled quantum states, could be seen as an incredibly integrated system. Its event horizon acts as a boundary that unifies everything within it into a single, complex entity. Could this vast internal network of information relationships constitute a mind? The scientific basis for these ideas is at present virtually non-existent. They are philosophical thought experiments that stretch known physics to its breaking point and beyond. There is no experiment we can perform, no observation we can make to test whether a black hole is conscious. The ideas are criticized for being untestable and for anthropomorphizing the cosmos, projecting human qualities onto utterly alien natural phenomena. Yet, these speculations capture the public imagination for a profound reason. They touch on our deepest questions about our own place in the universe. If a black hole can be conscious, then mind is not a rare accident on a lonely planet, but might be woven into the very structure of reality. It transforms the cosmos from a cold, mechanical clockwork into something more akin to a living, thinking entity. This vision offers a strange comfort, suggesting that in contemplating these dark giants, we are not just studying distant objects, but perhaps communicating with the universe's own hidden mind. While these ideas remain firmly in the realm of metaphysics, they serve a vital purpose. They remind us that the ultimate mystery may not be outside in the stars, but within the nature of awareness itself, and that the silent, all-consuming black hole might hold the final reflection of our own quest to understand. The silent, steady glow of Hawking radiation carries a death sentence written in quantum code. For all their immense power, supermassive black holes are not eternal. They are slowly, imperceptibly evaporating, leaking their mass and energy back into the cosmos one particle at a time. The process is almost unimaginably slow. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate, a number so vast it dwarfs the current age of the universe. For a supermassive black hole weighing billions of solar masses, the timeline stretches to a googol years, a 1 followed by 100 zeros. This is a timescale where stars have long since burned out and galaxies have faded to darkness. In this unimaginably distant era, the evaporation will finally accelerate, As a black hole shrinks, its temperature rises, causing it to radiate away its remaining mass faster and faster. In its final second, it would release the energy of 1 billion nuclear bombs in a silent flash of light, leaving behind nothing but empty, expanding space. This ultimate fate is inextricably linked to the destiny of the cosmos itself. If dark energy continues to accelerate the universe's expansion, leading to a cold, empty Big Freeze, then the evaporation of the last black holes will be one of the final significant events before reality settles into a permanent, timeless equilibrium. But what if that final flash is not an end, but a new beginning? One of the most speculative and beautiful ideas in cosmology suggests that the interior of a black hole could be a portal to a new universe. In this view, the collapse of matter into a singularity is not a dead end, but a cosmic bounce, a rebound that births an entire new cosmos with its own laws of physics, hidden forever within the event horizon of its parent universe. Our own Big Bang, from this perspective, could have been the white hole eruption from a black hole in another reality. This leads to the concept of a cyclic universe, an endless cascade of cosmic generations. In one model, when a black hole evaporates completely, it does not vanish. Instead, the information it contained, perfectly preserved, becomes the seed for a new inflationary epoch, a new Big Bang. Our entire universe, with all its galaxies and stars, could be the elaborate afterlife of a black hole that died in a previous cosmic cycle. These ideas are, for now, untestable poetry written in the language of theoretical physics. Yet they transform the black hole from a destructive monster into a potential cosmic midwife, a recycler of reality. Its silent, patient decay over eons might not be an epitaph, but the first verse of a new cosmic story, one where death is merely a transition in an infinite cycle of creation. Our journey through 30 cosmic riddles brings us full circle, from the impossible birth of these giants to their speculative, universe-spanning end. We have stood at the edge of the event horizon, wrestled with the ghost of lost information, and peered into the heart of singularities where physics itself falters. These are not merely astronomical curiosities, they are the bleeding edge of human knowledge, the places where our most trusted maps are marked with the warning, "Here be dragons." Each breakthrough, from the first image of a black hole's shadow to the faint hum of the gravitational wave background, does not simply provide an answer. It peels back a layer of the cosmic onion, revealing a deeper, more intricate puzzle beneath. This is the beautiful, relentless engine of science, where every solution births new and more profound questions. It is a reminder that the universe is far stranger, more wonderful, and more mysterious than we ever conceived. So we leave you with this final thought. Which of these 30 mysteries captured your imagination most completely? Was it the potential for wormholes, the fiery debate over the firewall, or the haunting possibility of a conscious cosmos? Let us know in the comments, and if this voyage into the unknown has sparked your curiosity, be sure to subscribe. Our exploration of the universe's greatest secrets has only just begun. These cosmic riddles are not just remote curiosities, they are profound reflections of the very questions that have defined our species. We have always looked to the stars and wondered about our place in the grand scheme, seeking to understand the rules that govern existence from the ground beneath our feet to the edge of the observable universe. Supermassive black holes are the ultimate expression of this quest. By studying these impossibly distant and extreme objects, we are not just exploring alien realms, we are stress-testing the very laws of physics that operate here on Earth. The same gravity that causes an apple to fall from a tree when taken to its absolute limit creates an event horizon. The quantum weirdness that governs the particles in a laboratory, when amplified by a black hole's immense power, threatens to erase information from reality itself. Every mystery we unravel about them is a direct probe into the fundamental forces that shape our everyday world, revealing a universe that is far more interconnected than it appears. Why do these dark voids captivate us so deeply? They are the universe's perfect paradox, embodying both creation and destruction, order and chaos, the known and the utterly unknowable. They are cosmic blank canvases onto which we project our deepest fascinations with mortality, infinity, and the nature of consciousness. In their silent, relentless pull, we see a metaphor for the unknown that beckons every human generation, the irresistible call to explore, to understand, and to push beyond the boundaries of the known. Our relentless pursuit of their secrets, building Earth-sized telescopes and listening for the faintest ripples in space-time, is a testament to an unquenchable curiosity. It is the same drive that painted on cave walls and launched sailing ships into uncharted oceans. Black holes remind us that we are not merely passive observers of the cosmos, but active participants in a grand, ongoing story of discovery, a species forever compelled to look into the darkness and ask what lies